So here we have practice problem 9. And this question says TP and TQ are tangents to the circle at P and Q respectively. Now pay careful attention to that. They mentioned two different tangents. So we've got tangent TP, here's TP, and we have tangent TQ. So there's two different tangents to the circle. Now they mentioned tangents, so we are thinking of tan chord, tan rad, those theorems. It says TY is drawn parallel to RQ. Here's your parallel lines, TY and RQ. The fact that you've got parallel lines, please think of fun X, okay? Corresponding, co-interior, alternate, think of all of that. And it says that Y is on RP, so yes, we see that on line RP, here's Y. Then it says angle TPQ is X, so follow that TPQ, it's actually P2. So TPQ is the same thing as P2, that is X. So we've got a lot of information to start off with. And the first question says, name with reasons 3 other angles equal to X. So we need 3 other angles that are equal to X. Now the best way to start off with this is for you to notice that angle X lies between a tangent and between a chord. So immediately we are thinking of tan chord. And remember how tan chord works? Tan chord says the angle between a tangent and a chord at its point of contact is equal to the angle subtended by the chord on the circumference of the circle. So if we want to know which other angle is equal to X, all we do is we follow the chord and we see what angle the chord creates on the circumference. So here we have angle R as X. So let's state that. Remember, we need to get 3, so this is our first one. We're going to say angle R is equal to X, and we made use of tan chord. Okay, let's get the next angle. So now that we know that angle R is X, I want to pay careful attention to the parallel lines. So here are our parallel lines, and I want you to focus on this F shape that it forms. And we know that the F shape means corresponding angles. So where we have angle R, we also have angle Y3 being the corresponding angle of angle R, which means that if angle R is X, Y3 is also X because corresponding angles are equal. So that is the second angle. Angle Y3 is X, and that is corresponding angles. Now let's look for the third angle that's equal to X. Now let us focus on the other tangent line. And at the same time, I'm going to focus on chord PQ. Why though? The reason why I'm focusing on PQ is because PQ subtends to angle R, which is X. And also, in terms of this tangent, we've got angle Q4 that lies between the tangent and between the chord PQ. And when we follow the chord PQ, it subtends to R, which is X, meaning that angle Q4 is X as well. This is because of tan chord. Okay, moving on to the next question. It says, prove that TPYQ is a cyclic quadrilateral. Let's actually find that shape. So here we have TPYQ. Here's the shape, TPYQ. And we need to prove that this is a cyclic quadrilateral. Now, you guys, there are three ways of proving that a quadrilateral is cyclic. And yes, I know you may be thinking it does not have a circle around it. How is it cyclic? So we think of there being an imaginary circle around this quadrilateral. So you can actually draw a circle around it, but if you know the three ways of how to prove a cyclic quad, then there's no need for you to draw a circle. So here are the three ways of how to prove that a quadrilateral is cyclic. And I'm pretty sure I've given this to you in one of the previous videos, but I'm just going to put it up here for your convenience. So here are the three ways that we can prove that a quadrilateral is cyclic. If we're able to show that the opposite angles are supplementary, then obviously it's a cyclic quad. Or if you can show that the exterior angle is equal to the interior opposite. Now the first two ways are quite simple, they're quite basic because they are the theorems for a cyclic quad anyway. But the third one is something a little out of the ordinary. If you are able to prove that you have angles in the same segment, then yes, it is a cyclic quad. Now this is actually the one that we are going to use for this question. And the reason why is because if you look at your diagram, here's your shape for angles in the same segment. Angles in the same segment almost always have this particular shape to it. And we can clearly see that in the cyclic quad, we have angle Q4 being x, angle Y3 being x, and notice that they are both subtended by P and T. So P and T subtend to Q4, P and T subtend to Y3. That is clearly angles in the same segment. And that is why it's only 2 marks. Because you just need to state those angles are equal, the reason why they're equal, and that due to that reason, it's a cyclic quad. So let's write this down. So we're going to say angle Q4 is equal to Y3, which is x. Now you can just say proven, okay? You've proven that they're equal to x. But now we're going to conclude and say, therefore, TPYQ is a cyclic quad. And now you write down your reason. We used angles in the same segment. So to prove that TY bisects PYQ, firstly, here is angle PYQ. If we follow PYQ, we see that it's made up of Y2 and Y3. So we basically need to show that Y2 and Y3 are equal to each other. If we show that they're equal to each other, then obviously, yes, YT has bisected that angle. So our aim is to show that Y2 is also X. Now, this is quite easy to do because you have already proven that TPYQ is a cyclic quad. And when you have a cyclic quad, you can use angles in the same segment. I want you guys to focus on points T and Q. And I want you to notice that T and Q subtend to P2. T and Q also subtend to Y2. Those are angles in the same segment, meaning that P2 and Y2 are equal to each other. And if P2 is X, then Y2 is also X. Now, seeing that Y2 and Y3 are both X, it means that angle PYQ was bisected by TY. So we can now state that for 12.2.3, we're going to state, firstly, let's mention that Y2 is X. Angle Y2 is X. That was from angles in the same segment. Then we're going to mention that angle Y2 is equal to angle Y3, which is X. Therefore, TY bisects, and the angle was called PYQ. So for that reason, the angle is bisected, because clearly y2 and y3 are equal to each other. So the entire angle PYQ has been cut in half. Next, we need to prove that triangle RQY is an isosceles triangle. Let's find this. RQY. Now, to prove that RQY is an isosceles triangle is quite simple, because you guys notice that RY and QY should be the sides that are equal, right? But something that you should not confuse is that Y is not the center of the circle. Okay, Y is not the center, but by looking at the triangle and having worked with isosceles triangles, we know that we should get Q2 to be X. But how are we going to do this? Let us focus on the parallel lines that we have. And from those parallel lines, I want you guys to notice that there is this N or Z shape that is formed, meaning angle Y2 being X would be the same as angle Q2. Okay? Angle Y2 is X, angle Q2 would be X because of alternate angles. Let's start off by mentioning that. So we're going to say angle Q2 is equal to X, and our reason for saying that is alternate angles. Then we're going to mention that because we have equal angles, the sides opposite them should be equal as well. But we can state the angles first, so we can say angle R is equal to angle Q2, which is X. Therefore, RY is equal to QY. RY is equal to QY. Therefore, triangle RQY is an isosceles triangle. And our reason for saying this is equal angles, opposite, equal sides. So that's it. We have proven that this is an isosceles triangle. We've shown that there are two sides equal. So here's our two sides equal and two angles equal.